Well, good morning. I'd like to welcome you to our celebration of Faculty Career Colloquium. This program is part of the College of Engineering's focus on faculty development, including for our most senior and successful folks. All right? So the way this works is a professor who's been here, who has been a full professor for at least 7 years, gives a presentation on their accomplishments over the years and their plans for the future. And the rest of us get to benefit from the opportunity to watch them and hear about what they've done and hopefully model some of our careers after what they've managed to do. Right? So our speaker today is Timothy Fisher. He came here in 2002 as Professor of Mechanical Engineering and working at the Burke Nanotechnology. In 2013, he was named the James G. Dwyer Professor in Mechanical Engineering. Today he's going to talk to us about the interdisciplinary science and engineering of carbon nanomaterials.
All right, Audine, thank you very much. I'm going to go ahead and dim this because I'm experimenting with Apple's Keynote, so I took one of their things, and I'm finding it's a lot easier to work with. I don't know if anyone else uses it, but I like it. So today, as Audine said, this is sort of a new program. It's been going on for a couple of years. I think it's really a good program. The one thing I would change about it, I would just call it what it is, which is the last line here, right? So this is part of post-tenure review. And we should have that. I mean, I don't think we should be afraid of it at all. The subtitle here, I'll get to that at the beginning. And I will also make an apology up front. It's a little bit rambling, and I thought long and hard about whether I should have this talk be driven by research and teaching, or whether I should have it be driven by people, and then talk about the research along the way. Mostly, what I ended up with is talking about people in a chronological format, more or less, and the technology and the science and the research along the way. So I'm going to start with where I began a little bit. I grew up in a town called Aurora, Illinois, which is famous for really only one thing, and that's Wayne's World. Okay, but if you actually watch any of the Wayne's World movies, I think they made a few. Only the first one is worth watching. They took a picture of the city limit sign, and that's really the only part of Aurora that's actually in that movie. There is no Stan Mikita donut shop or anything like that. I wish there were. Anyway, so before college, that's where I was, and one of the formative things about my entry into a career is the quote from my father, who is actually a Purdue graduate, and he told me that he would not pay for college unless I was an engineer. But he was not. He started out at Purdue as an engineer, and he would say he failed out of school. I think this is being recorded, so I really don't want to go a whole lot further down that path. But he did not fail out of school. There's a story behind it, and he just got a C in an 8-hour credit chemistry class, and my grandmother was not happy about that and said, your grades need to improve, and so he came back and transferred to Krannert. So I had a secret plan. I always have a secret plan, and my secret plan was to go to Cornell. I went there for a variety of reasons. Partly it was actually mostly because of baseball. But Cornell has a very good engineering physics program. So my secret plan was to go to a place that had sort of a hybrid engineering science program and sort of move into it after my freshman year. And so I tried to do that. And I said, Dad, I think I'm going to major in engineering physics. Is that okay? And he said, does that have the word physics in it? And he said, well, what do you think? And in his defense, this was at a time, this was the late 80s, at a time when Newsweek was writing articles about physicists flipping burgers at McDonald's, right? I mean, that was the theme. So anyway, I went from there. Most importantly, as an undergraduate, I did undergraduate research with a gentleman named Ken Torrance, who ultimately became my PhD advisor. And that was an experience that opened me up to research. And so, for all of you who participate in research here and think about whether you should take the time to to mentor undergraduate students. I know it's an extra time commitment, but it's well worth it. And so I try to remember that myself, even though I have to limit my appetite in that regard with so much else going on. But Ken was a wonderful mentor as an undergraduate. I did leave and I went to work for Motorola while my wife went to graduate school. And so I worked at Motorola north side of Chicago. And then after 2 years, I was really bored of doing engineering, even though Motorola, I know today the young people think it's a sort of dying company. At that time, it was like it was winning all the awards for best company to work for. It was the place to be. It was exciting, but what I realized is that if you wanted to really move through the system, then you would have to go into the management track, and you do a night and evening MBA at Northwestern or University of Chicago. And I didn't really want to do that. I wanted to stay with the technology. So Amy, my wife, and I took a vow of poverty and went back to grad school. And since I knew Ken so well, we stuck with him as my advisor. The SRC funded my graduate program entirely. I was an SRC fellow even before I matriculated for graduate school, so that was really nice to have that fellowship running along. And so in graduate school, and this is a surprise to a lot of people who know what I do today but not what I did before, my PhD thesis was on chimney flow, the exciting world of chimney flow, okay? And this is I actually built this and modeled that, and I'm very proud of it. It was interesting work, and something useful came out of it. And I could talk about that, but it's certainly not micro nano. It was not the kind of thing that's going to make the cover of a journal. But it was very solid work, and I learned how to do research from Ken. Along the way, I also learned how to teach. Ken himself was a very good teacher, but I had the privilege of learning almost all of my graduate math from Subrata Mukherjee. At Cornell, they teach graduate math through what was the Theoretical and Applied Mechanics department. So I had 2 courses on math with Subrata, and then 1 on boundary and finite element methods. And he's just an amazing teacher. Both of them, well, Subrata's retired. Ken passed away a few years ago. But one thing that Ken did is he knew he had a good vision for what was coming. He said, Tim, I'm going to have you work on chimney flow.
SRC supported your work on chimney flow?
So do you remember so the question is, did the SRC support my work on chimney flow? Do you remember the Apple Cube computer? It was fanless, and it had these big fat grommets. You know what's in the middle of that thing? A chimney. It's fanless. There's a chimney in there. So Ken said, look, Tim, I don't know how far this is going to take you. You need to learn about this. He didn't even say nano then, micro stuff. And so he had me go take statistical thermodynamics and solid state physics. Al Sievers taught me solid state physics, a wonderful teacher also. I will also mention, I had a life also while I was a graduate student, and I try to remember that when I deal with my own graduate students, but I did a lot of other things. I was also the assistant varsity baseball coach, so that's a 20-plus hour commitment every week, and Ken fought me tooth and nail to do that. But then I reminded him, I met Ken Torrance early on a Saturday, way too early on a Saturday morning when I was 17 years old, on my baseball recruiting trip to Cornell. And I said, Ken, I wouldn't be here at all without Cornell baseball. And so that argument won the day. I was also the house dad, my wife was the house mom, at Kappa Kappa Gamma sorority. So my sons, who are in this picture, that was actually just kind of across the street from the sorority. So we had kids early, which it's a good time to have kids, except for the money thing. But we managed, and they're all okay. But actually, both of these are young men now, and they are students at Purdue. So on the left, that's Mark. He's a chemistry major, a freshman. Thomas on the right is an ag econ major. He's a junior. You'll see them again as we come through. So a week after I defended my PhD, I started my faculty job at Vanderbilt. And 2 weeks after that, I had a sit-down meeting with the dean. And this is the quote. Ken Galloway, I will say he's certainly the best academic administrator that I've ever met, tied with many maybe, but this is his quote. So Ken is an electrical engineer, actually does radiation effects. And he said, and he thought that he knew about electronics cooling, which is kind of what I did. And he sat me down in his, anyone who knows Ken, does anyone know Ken Galloway? Do you know him a little bit? He's now the president of ASEE, I think, as a retirement post. And he's very gruff, occasionally profane. He sat me down, he's very intimidating, and said, basically, if you don't start thinking about something different to do, you're going to fail here. And of course, my response was, why did you hire me, right? And he said that people thought that I had some talent, and so go find something else to do. But don't do electronic schooling. That was his advice. It turned out to be good advice, except I didn't really know much else. I didn't do a postdoc, and Cornell's sort of in this insular world. And so I just would walk back and forth to campus. We lived close enough to walk, and I would think, what am I going to do in my career? Day after day, walking back and forth. Well, I met a guy, Jimmy Davidson. We call him Diamond Jimmy, because Jim Davidson, every problem in the world can be solved by Diamond, according to Jim Davidson. And he's tried it all. Great guy, a good mentor, and somebody who said, well, Tim, let's try some heat. Diamond has good heat things, and so let's try it with heat. And that's kind of where we started, and I learned a little bit about synthesis. I didn't really stay there long enough to kind of bring that all the way to fruition. We had some work on electron emission that I'll talk about a little bit later, at least the follow-on work from that. But at Vanderbilt, we added the third. Actually, Grace, she's on the left there, was almost born when I defended my PhD. So this is, lots of young kids, new faculty member, dad sitting there writing proposals and kids vomiting on the proposal, because we'd do things by handwriting a lot of times back then. But most importantly, I had a wife who was extremely supportive and is always a great mother and spouse. And so we soldiered through. But then in 2002, Purdue came calling, and the first time around, it was with Dan Hurleman and Jay Gore. They contacted me, and they said, we want to do nano, and we need some experimentalists to do nano to help support our already strong, very strong theory group led by Mark Lundstrom, Supriya Dado. You'll hear about them later. But that was before the Burke donation happened. And so there were a lot of universities at the time, if you remember this back in 2002, who were talking about nano a lot. And then you ask the next question, well, how much are you going to invest? How much do you have? And almost all of them said, well, that's just around the corner. We'll have it soon. Well, I'd gone through that as a baseball recruit, because at Cornell, they had told me when I was in high school that they were going to have this wonderful indoor baseball practice facility. And as you might imagine, in Ithaca, New York, that's really an important thing to have. And so they said, it's going to be here next year. It's going to be here next year. And they didn't have the money for it when they recruited me. I didn't know this. I was 17 years old. And that indoor baseball facility didn't show up until the end of my senior year in college. So we spent, basically we were practicing in an indoor gymnasium. And if it was even above 25 degrees Fahrenheit, we were outside to practice. And so I didn't want to be doing nanotechnology in 25 degrees Fahrenheit cold, right? And so I said no, and my extended family was not happy, my father in particular, as you might imagine. But then I think what happened, I don't know all the inner workings, I think what happened was as soon as they had the commitment from Mr. and Mrs. Burke secured, they came back to me. So this is just 6 months later. And we had a clandestine recruitment weekend. I brought my family up. I wanted to kind of keep this one quiet because the last time around it got kind of crazy down at Vanderbilt. And my immediate family this time was not happy. We decided to move, but I would say my family wasn't all for it. I mean, Nashville's a really nice place to live, except this time of year. Allergy season is terrible down there, but otherwise a great place to live. But the draw of Purdue and the opportunity to do nanotechnology was too much for me. There's one other thing that happened, which is very rare. I'm sure it's happened before, but I haven't heard about it, and that's this. I was actually given, I was a fully mechanical engineering hire, I was given lab space in the ECE building by Kent Fox because he knew that they needed somebody to do carbon nano things, okay? And I've not heard anything like that before. It's probably happened, but it's really a testament to Kent. Now, Kent's gone on from here to do many other great things. I think he's now down at University of Florida as the president or chancellor. But it was really amazing that another department gave lab space to someone completely outside the department. So this is what we did with the kids. We dressed them up. They become mannequins for Christmas cards, and so we have lots of these things going on, and had a good time. And I think it's fair to say everyone is happy that we moved here, except maybe my daughter, who now she thinks about Nashville and she could be a star, that kind of thing. But she can still move to Nashville later if she wants. All right, so I showed up, and they want me to do nanotechnology. Now, I'm not the guy who has this long history. Remember, I'm only a few years removed from chimneys. And now I'm supposed to be the savior for nanotechnology. And Supriyo Datta and Rashid Bashir, who's now at the University of Illinois, showed me this cartoon in a proposal that was funded, that just had become funded as I was moving here. And they said, Tim, we need to make this because this was in our proposal. We want you to do it. And I said, okay, I'll work on that. Who made the cartoon? And Rashid said, well, I made it. And I said, okay, well, what do you plan to actually do the growth? Where are things? He said, no, it's just a cartoon. And so it's all up to you to make this thing. And that was my first project, and yeah, it was scary. But remember, I already had the Ken Galloway treatment, so I was a little bit maybe mentally stronger than the typical thing. I had a lot of really good patient mentors. I think that's super important in the way that that academic research is conducted these days. That mentors don't expect young people just starting out to be as fast, to be as productive right away as they are in their current state. It's easy to forget that. But I had very patient mentors along the way. And we also were at the time planning the Burke Center, and I also had, it was wonderful to be with such an inviting group of people. So I had a seat at the table. I was a new guy, but yet they treated me like one of the gang, and we all mapped out the space, and we, where do the gas lines go, all that. There's a lot of intricate complexity to planning something like a nanotechnology building. So we built it. And I had the good fortune of sitting next to Tim Sands in the Burke Center. He was in the room right next to me, although he always says it felt like I was in his room. And I rarely walked in there, but I guess the walls are thin or something like that. Anyway, Tim is well known for a lot of work in materials, but one of them is this porous anodic alumina. And so he had these templates that we could use. And what we ended up doing to make this vertical carbon nanotube device from the cartoon is we buried a catalyst layer, that's the little green stripe right here, into the porous anodic alumina. We got lucky that even though it shouldn't necessarily happen that the pores kind of go through that layer, because all this starts out as a bunch of metal stacks and then we anodize. But it did. Matt Moshman is the one who showed that. He was a wonderful PhD student. He's now on the faculty at University of Missouri. And then we filled it. We grew nanotubes coming out of the pores, and we surrounded those with, in this case, that's glass coming through, and you can kind of see it. It actually looks, at least from the top view, a lot like what they wanted. There's a gate around the nanotube, and there are serious issues. We didn't get a whole lot further past this because the project had run its course. NASA pulled back the money early, not because of performance, but because it's NASA, I think. But Aaron Franklin and Dave Lubelski were integral to this. Dave is a staff member at the Burke Center, has been around a long, long time. Dave Janes was also associated with the work as well. Aaron was in the lab constantly. He's the record setter at the Burke Center. He racked up, he's the reason that there's a monetary cap per student. He racked up $75,000 between January and August in Burke Center fees. And I so kind of went to Tim and said, what are we going to do about this guy? And he said, well, just let him go. We'll cap it and we'll figure out what to do later. There are still serious issues with this, so I want to talk a little bit about technical things. So I don't think anyone's really figured out how to do chirality control. So that's the type of conducting that the nanotube does, whether it's a semiconductor or a metal or semi-metal. At least in situ growth, you can separate it afterwards and then sprinkle it around. Separate, filter, then reapply. But that's not a very efficient process. We always had issues with how many of the holes are filled with nanotubes, right? So we never got to 100%. We got to maybe 50%. And then optimizing the gate structure for a vertical device is still something that would be left undone. What happened more or less with carbon nanotubes, whether they be vertical or horizontal, is people figured out that they might be good in a sort of collective sense for low-end transistors, but then this thing called graphene came along and it pulled a whole bunch of people away from the nanotube transistor world into this next new thing. We did that too, but not so much on devices. So then that was my kind of beginning stage into nanotechnology, and I wanted to do more other things, in general things that are closer to my training. And so we asked this question. This is actually while I was on sabbatical. I'll talk about that later. I always want to ask the question, is newer always better, right? Or are we just doing it because it's new? This is an example where that's our driver repairing the truck as the camel cart goes by, right? So it's important to ask that question up front. The other thing about nano, at least in the real world, is that there's a lot of issues that I think are underappreciated. I'll articulate those in a moment, but in general, this is not just restricted to nanotechnology. Interfaces and boundaries are difficult places in general, right? So there's a interface or boundary that's a difficult place in the world, right? I spend a lot of time in those kind of queues, right, for visa processing and so forth. But in biological things, the interface is everything. Cellular structure, transport, sensing, it all happens around interfaces. So that's kind of where I went with nanotechnology, trying to focus on that. I had a mind to download a vision chart, right? There's so many of them out there for grand challenge problems. But I think it's fair to say nano touches just about all of the technical grand challenge problems. And so just pick your favorite one, and you could talk to me afterwards about how nano really, really touches it in a deep and genuine way. But there are a number of underappreciated challenges. These are things that that sit at the convergence of science and engineering. So those are interfaces and the transport across interfaces. So a single nano element can have a great property, but if you start to connect it to the real world or ask a bunch of them to work together, then not so much. And so this is where we need to do better engineering. Asking them to work together is also part of statistical mechanics, right? So we need to get a better understanding of variability, uncertainty, and so forth if we're going to do something useful with nano. And then physical and what I call cost scalability. It's great that you can make a single nanotube transistor that has the highest transconductance ever recorded, but if you can't do that a billion times, and if you don't have any idea how you could get there, then it's probably a science project. And so how do we get to a filter up front that says, I think that this is a really good technology at the nanoscale, and I also think it can scale up. And we need to do better at that. So I told you I work on heat transfer, and so I applied our new capability to grow nanostructures and carbon nanotubes in particular, and we started using them for thermal interfaces. So this is like a Velcro type thing that instead of sticking mechanically, although sometimes it does, it conducts heat across the interface better than most things, and I'll talk about that. So here's where we start with, this is a lot of fun work and great people associated with this. Sean Fan Shu, I'm not sure, is Sean Fan in the audience today? He said he was going to come. It's too bad for him. Embarrassing story about Sean Fan. I'm just kidding. No, I won't do that. He's a wonderful mentor. He's, I think, the best experimentalist certainly that I know. Jun Shu was the graduate student who did it first. Barakola and Placidus Amama, they're shown down here. They also kind of picked up from where Jun Shu had worked. And today we have Stephen Hodson and Menglong Hao. They're in the audience here. So this has been a sort of a journey, and I'm only going to spend one slide on it. But this is what a carbon nanotube thermal interface looks like. Right? So it's not quite so easy to see, but it's a forest of carbon nanotubes. Carbon nanotubes themselves have individually very high thermal conductivity. People argue about what it is, and of course it's not one thing. It depends on lots of things like atomic structure and defects and so forth, but you could think of it as being about 1,000 units of thermal conductivity. Those are watts per meter Kelvin, typically. But these forests are only a few percent dense, and so you have to downgrade that by a factor of 10 to 100. You get to a point where it's good but not great. Maybe the best thing about the nanotubes is that they're very mechanically compliant. So this also gets back to kind of my core discipline, where we do some mechanics of the problem. And now it's a multi-physics approach, and multi-physics benefits from having something like this. Now, we hired a new faculty member, Amy Martinet. She'll show up again, but she's done a really nice review study of nanotubes, and this is a bit of an eye chart, but basically breaking down the different elements of thermal resistance. And there's a bunch of different studies, some of which, about a third of which are ours. And the point here, this is that scale of conductance. Everybody wants to have a total resistance right here at 1 unit of resistance. This is millimeter squared Kelvin per watt. That would be 1 millimeter squared Kelvin per watt would mean that you'd have 1 degree temperature rise across the interface if you were burning 100 watts per square centimeter. So that I'm pointing to the electrical engineers, they can get that. That's what people want. And you can see that even the individual elements on almost all of these things are above that. And so you have to add, these are series resistances. If you start to do things like solder it together, then you can get down low. But then you ask the question, why don't you just put solder there in the first place? Because you know you're going to get that. The answer is solder has terrible mechanical properties. So this is a balance, again, between electrical and, well, sometimes electrical, but thermal and mechanical behavior. Again, more heat transfer. We said, well, we can make these carpets, and people want to have, boiling happens all over the place, right? It's not just about cooking pasta, right? It's in power plants, it's in all kinds, it's in your air conditioning. And so can we make a surface where boiling is more efficient? That's the question that we asked. And I had the privilege, another wonderful mentor, Issam Mudawar. He's been here since the early 80s. He is, certainly in my opinion and many, many others, the best person in two-phase heat transfer who's active in research today. And then a couple of students, Sebastian Ujeri, who I brought up here from Vanderbilt, and Arun Kosalia as well. And so we looked at this problem, and the question is, if you just took, say, a bare piece of silicon, let's say that you wanted to boil in order to cool silicon, you'd get a boiling curve that looks like this. Now, what you want, so this is heat flux, you want the highest amount of heat flux with the lowest temperature rise, so you want to be pushing to that edge. Silicon is not very good, but we already knew that. There's a little bit of straw man in this study, because silicon we already know is bad, so we're making something bad better. But the surprising part about this, you almost never see this straight vertical rise. So what this vertical rise says is that it doesn't matter how much heat flux I'm putting in, I'm basically going to have the same surface temperature. That you don't see too often, and that's a big effect. The problem with carbon nanotubes in this application is, how would you scale it up, especially for a power plant type of operation? Can you coat carbon nanotubes and keep them pinned down for the whole time that they're supposed to work, which would mean decades? And that one, no one's really studied it too much, but this is a good start. One of the things you'd want to do technologically is get this level of heat flux up. So these maxes mean that something bad happened at that point. Then we had burnout, critical heat flux reached, where you're boiling so much that you create a vapor layer that becomes thermally insulating over the surface. So then at the same time, right around these studies, I was wanting to do a little bit more in science. Again, I had this sort of pull from before college. And I met a guy who's shown in the first picture here, Ron Reifenberger, who has also been a wonderful mentor to me. But Ron and I first connected not at all on science. We connected with baseball, right? Ron is a baseball junkie. I am too. And so we would just talk about baseball mostly. A little bit about science, and then a lot about administration. But anyway, Ron is fantastic. He's also a wonderful experimentalist. Other folks that Ron is in physics. Chuck Lukart, I maintained a bit of a collaboration with him at Vanderbilt. He's a chemist at Vanderbilt. Greg Swain is a chemist at Michigan State. And then had a bunch of students. Vance doesn't like his picture to be shown, so Vance Robinson, he's at GE now. David Goh is a faculty member at Notre Dame, and Patrick McCarthy is a recent PhD graduate. He works for a consulting software company here in town. But we wanted to do electron emission. I could tell, again, a whole story about every one of these topics, but what you'll see as a theme is that when we looked at the more scientific things, what we tried to do is to bring it back to something thermal in the work. And so in this case, what we had was these are electron energy distribution measurements. We heated a sample. In this case, it's diamond. We heated a diamond sample that had been treated in hydrogen by us, and at first, as we raised the temperature, we had an energy distribution that looked like this. So we measured the distribution of electron energies that were shooting out of this material, basically boiling out of this material, and we had this type of distribution. Well, you actually want to have a low energy emission. There's a barrier that sits here called the work function or the electron affinity. And you actually want to get that to be lower and lower so that you could use it, for example, in an electron source, as an electron source, or maybe in an energy conversion process. And so you want to push this lower. And so by doing the hydrogen termination, we were able to do that. But then we raised the temperature, right? So we went to 900, and as soon as we got to around between 800 and 900, the barrier shifted. What happened? The hydrogen left the surface. The work function went up by a lot, right? It went up by almost a whole electron, an entire electron volt. And then when we brought the temperature back down, it stayed up there. So that means that there was an irreversible process done to the surface thermally. So this is where we're trying to get more thermal things going on with science, sort of matching the two. Now, at that point in time, so this was around 2008, it was time for me to take a sabbatical, and we talked about it. We sort of rushed the planning because our oldest would have been in 8th grade, that's Thomas, and we didn't want to pull him out of high school, so we kind of pulled this thing together. Obviously, the main purposes of a sabbatical, the main purpose is to expand yourself professionally, and I think we need to take that seriously as faculty members. For me, this sabbatical leave made a huge difference, as I'll explain. But also for us, we decided we wanted to show our children a new culture, and so we did this. So how do we put that together? Well, it's a long and sordid tale, but I will tell you that we were in India. This is actually a Purdue mechanical engineering alum who owns a restaurant called Indiana, and we were touring around, and we said, well, we should go to that restaurant, right? It was one of the best we ate at. It turns out that the owner had a long career in Indian Oil. He's a Purdue Mechanical Engineering alum, and this is sort of his retirement gig as he's running a restaurant in Jaipur. And so that was a wonderful thing. It just totally stumbled upon. We also did the typical thing, right? So you have to have the Taj Mahal picture if you go to India. But also, Amy, my wife, and children spent time volunteering with a school that served slum children, and that was an extremely rewarding experience for her and for us. And then we also had our going away party, and they gave us, some kind of. It's a great honor to wear a gold turban, I'm told. So that's what happened. Incidentally, Indumati Rao, this is C.N.R. Rao's wife. She's also a Purdue graduate. She has a master's degree in education, and so they were our hosts. I'll talk more about them as we go through. So here's a picture of C.N.R. So while I was in India, there are virtually no engineers at the Institute. Jawaharlal Nehru Center for Advanced Scientific Research, I'll call that JNC. C.N.R. Rao, a Purdue graduate, founded that. He's one of the most preeminent scientists in the history of India. He won the Bharat Ratna, which is the biggest civilian award that you can win in India. He won it last year, along with the greatest cricket player in India history. So if you know anything about India and cricket, you'll know that that's a big deal for him to also win. And then I met a whole bunch of wonderful people. Giri Kulkarni was formerly my host while I was there, and I couldn't have asked for a better person to help me. And today I can't ask for a better friend than him. But there's also all sorts of other folks. I'll highlight them as I go through this. One of the things we did in scalable chemistry, this is work with Kulkarni, is we were interested in doing carbon nanotubes, but using some self-assembled chemistry along the way that Kulkarni was working on. So here's a carbon nanotube. You can hardly see it. But he has this palladium ink that he had developed to make contacts to an individual carbon nanotube. Here's my favorite kind of IV curve, right? Nice and linear. I don't, all the curves and things like that, they confuse me. So you can see that this thing works really well. And what we did is, again, getting back to that thermal thing, is I said, well, I don't really care about a linear IV curve. I want to break things. And so we would burn up the carbon nanotubes and then do the thermal modeling on that. And it would tell us a lot about the structure, the likely temperature ranges that the nanotube was experiencing. And of course, if you're ever going to make a technology out of something, you have to push it to the limits. Electrical engineers will always push current to the limits in devices. And so this was sort of a start of a series of other similar work that we've done with Kulkarni and his group. I also learned for the first time about atomistic physics. So this is density functional theory and some other things. Umesh Wagmare is a physics professor. He's actually in the theoretical sciences unit at JNC. One of the best in the world. He won the top physicist under 45 award in India a couple years ago. Ricardo Grau Crespo he's at Reading University now, but he was on leave at JNC at the time, so we sat around and talked. The tea table at JNC is one of the best places to go if you want to do some interesting science. So, and then Shobhana Narasimhan, also a wonderful theorist and condensed matter physicist. So, some of the things. This is just an example that sort of again stays with the theme. We looked at diffusion of defects in magnesium hydride. Why is that important? Well, magnesium hydride is a metal hydride that could be used potentially for hydrogen storage or for solid state heat pumping. The problem with it is that it's slow and it doesn't work at high temperatures. And so in this case, what we were doing is studies of integrating lithium, how lithium, essentially as a dopant, can affect the defect density. And then the things that we start to add to the study are, let's look at this at different temperatures and understand how the defect density works, because the defect density is going to dictate, in the end, the hydrogen diffusion rates in this material, which are the limiting factor for its technological use. And so that was interesting. We ended up doing some bigger scale things, and I'll talk a bit more about this later, but with Kyle Smith, he was a student, an undergraduate. I think he was the top undergraduate student in mechanical engineering, and he had done some undergraduate research with me, and he said, you know, I want to go to graduate school, but I'm told that you should go to a different place for graduate school. And on the spot, when he said that, I said, Kyle, if you come to graduate school here, I promise you that I'll send you to an exotic foreign place for part of your graduate study. I had no idea how that was going to happen, because this was even before my sabbatical leave. And so I ended up taking Kyle along with the family on our sabbatical leave. I'll describe some of the work he's done. He's an assistant professor at the University of Illinois now. And the person in the top right, he's the one who taught us about granular mechanics. It was a subject that was completely foreign to me. It all started at the tea table at JNC. Kyle said, hey, you know, I was getting tea, and this faculty member, Mehboob, is working on granular mechanics, and I think I can do some interesting things with it. Is it okay if I try? And I said, Kyle, I mean, you know, we have all these other things going on. He said, well, just give me a week to do it. And that led to a whole bunch of other work that's being carried forward by Ishan Srivastava, who's in the back here. He's a senior PhD student in the group. And in this case, so this is a busy chart, but what we've done, and in short, is granular mechanics as a field largely was one of two flavors. The mathematicians usually took idealized structures and then analyzed them to a very great depth. Idealizations meaning like especially 2 dimensions, or if it was 3 dimensions, it was always nice smooth surfaces. And Kyle was interested in those metal hydrides, and he said, well, they're not smooth surfaces, they're faceted. And no one does 3D faceted particles, and I think I can do it with Mehboob's help. And so we started that. This is a metal hydride. This is a simulation. I'll actually show you a little bit more of that. Here's another interesting material. Those are very thin, high aspect ratio nanoplatelets that are used for thermoelectrics. So we can simulate something and have at least a significant similarity to reality. We're also doing this for carbon nanotube arrays, so getting back to that combination of mechanics and thermal for carbon nanotubes. And then also, we do a lot of things still in idealized systems for polydispersed spheres and uniform spheres. So here's a simulation. Let me see if I can get that bigger. This is how we simulate. This is all mechanics. This is how we simulate the structures here. There's a lot that goes into it. There's more physics still to add. These are frictionless. It's athermal, meaning it's essentially not thermally agitated. But we predict structures like this in the computer, do all the things that you're supposed to do about grid independence or size independence. We can predict these structures, and then because we care about transport, we take this structure and we then simulate the flow of heat through that material. Again, it's a metal hydride that can be used for thermal storage or a thermally activated hydrogen storage. And so it sort of runs the gamut from the very basics all the way up to the transport problem. And I'll talk about that also a little bit more at the end. So just thinking about global a little bit, this is a chart. We started a joint center. After I got back from sabbatical, we started a joint center. And I really don't like paper counting, but usually sponsors insist on it, and they ask, well, how much are you two connected? So this is our most recent publication network between JNC and Purdue, and you can see that there's actually quite a bit of interaction. Not as much as I would like. Sorry about this. I'll have to get back. I don't know how you sped through. There you go. And of course, there's, I spend about a month or more per year in India. Kulkarni is the other main person in JNC, and he spends a lot of time here as well. And so he's developed a lot of collaborations, as have I. But still, there's a lot of activity going on here. In fact, many of these lines have many papers in them, and there's also a bunch of new folks who I'm hoping to bring along, one of whom is in the audience today. So here's an example. This is what happens when you go to India. This is Greg Shaver. I don't have his name listed on here, but this is what happens when you go to India. I went to on a sort of a tour of Indian institutions with Greg to try to promote some online teaching materials. And every place we went, the students congregated around Greg. He was talking about hybrid vehicles. I was talking about heat transfer, which is almost as bad as talking about chimneys, right? So I would be standing here. I had lots of time. I could take pictures of, so I took this picture of all the students around Greg. But that happens. They're so eager to learn. They're eager for more. They have a deficit of faculty. They have a deficit of institutions to teach technology and to do research. This happens every place we go. That's a good reason for us to keep connecting. So when I came back, to Purdue, for some reason I immediately jumped away again. Not because I don't like Purdue. I actually like it quite a bit. But I wanted to do some things with a research lab in the US, and Byron Pipes had this idea that he wanted to start a defense institute. And he said, Tim, what you need to do is to go to one of the defense labs and really get yourself integrated. You'll learn a lot about their needs, things that you just can't learn from their open calls for research. And so I did that. It turns out that they were at Wright-Patterson Air Force Base. They were just starting a new branch. That's like a small department in thermal materials. And so Andre Vivodin, Ajit Roy are the principals there. Nick Lavin was a student there at the time. He's still at Wright-Pat, but he's a PhD student, distance learner from Purdue. We did a lot of different things. Here's an example of something we did with graphene. So on the left, you'll see this is a paper from Science where they did the growth, and it took about half an hour to do the growth, over 2 hours to do the whole thing. And we used a plasma technique, so that's the expertise of Andre and mine, and we cut that down to just 10 or 20 minutes. So those are some of the things that we were working on then for scalability in nanomaterials. Then one day, when I was at the Air Force, I would spend Monday through Thursday at Wright-Patterson and then come back here and work Friday and Saturday and Sunday and have very little time for anything else. But one of the days I came back, I was doing some training. I was training a couple of people on using our microwave plasma system, and a guy at the Air Force, Roger, he's over here, he doesn't like his picture taken either. He gave me some carbon fibers and said, Tim, why don't you put those in your chamber and see what happens? And so we did. And Bhuvana was a postdoc. Anurag Kumar is a student here. Chandra Bose is a great friend. Interesting story about Chandra Bose. He's a faculty member at JNC, and so he helped us with the Raman characterization of these. But Chandra Bose was a postdoc at Cornell when I was a graduate student. Our kids were in the same daycare. So that's a small world all the way back here. And then Dima is our surface scientist. And so petals. You've probably seen something about these. So on the top left here, you have flat graphene. It's got some grain boundaries. If you keep growing, at least in our system, you start to go vertical with those, and you get these beautiful petals. The first thing we did was to grow them on carbon fibers, as I said before, but now we put them on all sorts of different things and applied them in many different ways that I'll describe. So one of the first things we did was to work on bio. I don't know much about bio. The last biology course I took, I was 14 years old, and I slept through most of it. But Marshall Porterfield was a wonderful collaborator at the time. He's now at NASA. Jonathan Clausen was the main student, and then we have Bumsu Han, who we're starting to do some interesting things with for petals and cell growth. But what happened in essence is we took the petals and we functionalized them with different amounts of platinum, and it turns out, and this is really just dumb luck, it turns out that they have this wonderfully wide linear sensing range that covers all of the main bodily fluids. There's nothing really like that out there, at least for amperometric sensing. And the sensitivity is extremely high, not just the linearity, but the sensitivity is extremely high. And so this was work that caught a lot of attention. And people ask me, well, how did you think of that? And I really said, well, you just looked at the petals and said, it looks kind of like a lot of things in biology and should catch, targets that you want to sense. And in fact, it did. We did a little bit of engineering on this, sort of the surface metallization and some of the surface chemistry, but otherwise, it's all just natural. Then we had started to apply it to energy. This is Guoping Xiong. Ron, of course, is always there with sort of in the background for us as our science sounding board. Pedro, I think in biomedical engineering, they only take like action shots. There's no boring headshot. So Pedro, this is Pedro. He started to collaborate with us. This has nothing to do with bio. It's all about energy. But we ended up using the petals, making samples. I love this picture. This is a LED, a green LED that we're lighting using a real engineering human scale supercapacitor. And this was the result of a nickel bet. So Ron Reifenberger, one of the ways that he motivates students is to bet them a nickel that they can't do what they claim to be able to do. And so Ron bet Guoping a nickel. And I think Ron still thinks that a nickel's a lot of money. I'm not sure about that. But that he couldn't keep this LED lit for half an hour, and Guoping did. So Guoping is now a nickel richer than he used to be. There's a lot of other stuff. I'm going to start to wrap up here in just a bit, at least to get to some other things. We're trying to do better modeling of nano. So I think that's a big, if we want to scale up, if we want to understand the statistics, we need to do better at modeling. We're trying. We have some wonderful collaborators. Jayati Murthy was here until a few years ago as a modeler, and she's just amazing. Shulin Ruan. We started to collaborate with the NanoHub people, Gerhard and Tillman. Sridhar, Dhruv are students that have worked on this, and Sabri Kais is a chemistry professor at Purdue who's been spending a lot of time in the Middle East, but we've started to collaborate with them. So I'm just going to show you a few examples. On the left here, this is a very recent paper. So we want to study the transport of heat across a metal semiconductor interface. This is tisilicide and silicon, which is used in industry. And people don't really understand how heat flows through all of the different carriers, because the dominant carrier on this side, the metal side, are electrons, and the dominant carriers are phonons here. And we're starting to, with some very good work out of Sridhar, starting to calculate things. This is the Eliashberg function. It's essentially the electron-phonon coupling factor in these materials, and then translating that into a thermal conductance across the interface. And this is all done atomistically. And that's, I think, a very, very important thing. If you accept the notion that interfaces are crucial to understand quantitatively for nanotechnology to scale up, then this is the kind of thing you have to do. And we looked long and hard for other people who had done this. We couldn't find it, and so we said, let's just do it ourselves. And that's really what we do when we model. We certainly don't want to reinvent wheels. We don't have time. Another thing that we've done on the mechanics side is we have done the heat transfer and the mechanical deformation of carbon nanotube arrays. And Sridhar is also the student working on this. So we do the full mechanics. This is coarse grain molecular dynamics. But we take a simulation like this, and then we get a final microstructure, and we can model the transport through that, as opposed to guessing at what the microstructure might be. There's all kinds of things that can happen here. Just, these things can buckle if they're a certain length and under certain stress conditions. And so being able to simulate it as opposed to try to do it physically and then measure it, and the only way to measure it is to use exotic instruments. It's much better, much easier to do modeling, and it's a huge help. We also are doing experimental diagnostics. This is with an eye towards scaling up. So Bob Lucht is a laser diagnostics expert. You've seen most of the other people. Alfredo is the student who started on this. He's just wonderful. I show him because he had such a heart for the community when he was here as a graduate student. He graduated last year. Was always doing some kind of volunteer work. Sergey Matret is somebody that we hired recently to do more and better diagnostics than most of the other folks. You'll see Majed on the bottom right is the student who's picked up Alfredo's work. But what do we do? What does it mean to do better diagnostics? Well, to me, this is just really complicated optics. Not only complicated, extremely expensive. So what I've learned to do diagnostics is you have to have a big bank account. And so Bob Lucht has a big bank account. Ali Shakuri does too, but he doesn't. I don't have the PIN code for it. But I mean, you can do amazing things. This is work that Nick Glavin, the student here, this was done actually at the Air Force. He's a PhD student here working from distance, doing diagnostics of plasmas in a nanosecond, with nanosecond resolution of the plasma plumes. And this is the kind of thing that you have to do to understand what's going on chemically inside of a deposition reactor to make a nano thing. So I'm going to, maybe 5 more minutes if I go quickly enough. I have to say that I am so I'm so humbled to work, especially with people like Mark and Supriyo and Ashraf, who've made this wonderful community for nano. So the same thing that attracted me here 15 years ago almost is the same thing that motivates me to go to work every day. I used to say, the Burke Center is the best place on earth to work. And now that I did this talk, what I really meant is that the nano community at Purdue is the best community I can imagine. And I'm so lucky to be here. They've made, I tried to think of the right word. It's really magical. All of the things, all of the opportunities that have come from what they planted and nurtured all these years. And undoubtedly, NanoHub has changed the world. I don't think the Burke Center has. I hope that it will. I hope it gets its act together. But certainly NanoHub has. Again, looking at what we might do on the experimental side, nanotechnology has an Achilles heel, right? And that is scalability, mostly. I talked about the other things, interfaces and statistics. So we need to do some surgery. So here's a wonderful group of folks. Ritu is a postdoc, George Chu. I called George the other day. My machine was acting funny. The control system wasn't working. I called him and said, George, I have a PID controller. It's going wacky. Can you help me? And he said, well, okay, what's P? And what's your P level? What's your I level? Yeah, try this. I tried it. It worked. It was amazing. John Coy was a staff member. He actually just left Purdue last week. Lena does some modeling. Guy tells Nikki, I wanted this picture in here. Guys in the audience. He's a staff member at Burke. We have to start building things and doing things. I mean, I hate to say that actually while I have a PowerPoint behind me, right? Because the PowerPoint's just too tempting. We have to actually build stuff, right? That's how people made great progress in research. We need to do more of it. Alex Way up at the top, our chemist, he's been a wonderful collaborator. What are we doing? Well, we're doing roll-to-roll nano things. So you take those petals and those fibers and you put them on a roll, and we're building a capability to take that web and put it in between 2 electrodes. This is a capacitively coupled plasma that's custom built, custom designed, blood, sweat, and tears, and you send the web through. We can make, in this process, more petals in an hour than we could make in a year in the old system. So that's another reason. My students don't like it when I say that, at least the ones who are taking the year to make the petals in the old system. I started and stopped a company. I'm just going to, a few lessons learned on this. It was basically a crash course MBA. I definitely don't need an MBA anymore. So lesson 1 is don't try to do a double startup. That means you're starting up a company with a startup venture firm. Bad idea. Lesson 2, which is really a persistent lesson, listen to your customers and adapt. So a lot of times we think about startup companies as being in this closed garage and they're going to create some great thing and then spring it on the world. It really doesn't work that way. You have to listen to your customers. Seek out advice from independent people and listen to it. That's also, same thing, get out in the real world. And the last one, and this is so tempting. It also happens with grad students. You can't download a vision from the web. Doesn't work that way. Right? Google's great for a lot of things, but if you think it's going to give you some kind of masterful vision of the world, whether it's a startup company or your research thesis topic, forget about it. Right? It can give you a couple of pointers, but that's it. You then have to go do and make things and try. All right, a few quasi-random thoughts. They're not really random, but that's why I put quasi there. All right. I'm known as a troublemaker. I don't know if that's a surprise to you, right? But I wanted to explain it. So every institution, actually institutions that are working have problems, right? Because there's new things happening. How do we address serious institutional issues? Well, this is the typical, not the only, administration position that I've heard, which is or seen, minimize how many people know about the problem, because that's probably going to reflect on me as the administrator, and make it go away as quietly as possible, even if you know it's going to come back, right? And then this always happens, right? You invoke the troublemaking faculty caricature, right? If you're ever pressed on this, that's just a faculty member. He's always making trouble, right? And then you can get away with it. You think, right? I don't think so. You don't get away with it with me. You don't get away with it with people like Paul Robinson. So Paul has inspired me. Fix the problem, right? Minimize the chance that the problem is going to happen again by fixing it the right way, openly, right? By the way, the openly is important. One of the ways to fix perpetual problems is to shame people, right? That's a well-known technique. It's not profound. So I think that we need to do a little bit more of that and less of hiding things. Next thing, are we creating a microcosm of a whole university in a single college? I think we're kind of close to that, right? So it's wonderful that we have this great hiring binge, and it's been great for faculty. I can eat 21 meals a day on Purdue's credit card, right? Because there's so many people cycling through to do interviews. Maybe not 20, maybe I could do 18 because we're not having people on Sundays usually. But I guess that's kind of nice. But so it looks like what we're doing to some extent is to strengthen interdisciplinarity by hiring interdisciplinary people into engineering. We're hiring people with science backgrounds, people with education backgrounds, even some social sciences, and that's okay. It's enriching us. There's no doubt about that. It's enriching us. I like it. Half of this talk is about science, right? What's not to like? Well, I think it certainly can create a local optimum for engineering. But the question is that taking us to a global optimum for Purdue? Is it good to do this for the disciplines or for the faculties themselves? One of the things I worry about, we're biting the hand that feeds us. If engineers' jobs are to take nascent discoveries from science and to translate them into technologies, what happens when that well is dry? And then, the bottom question is also important. Can a non-engineering discipline exist and be really a top-tier program while sitting in an engineering college? I don't know. Maybe there are some examples where that's worked. I couldn't think of any off the top of my head. But I think these are just questions, right? Again, it's not troublemaking. It's questions. I'd like to hear answers. I'd like the faculty to discuss these things. The faculty don't discuss these things at Purdue very much. So here are some good ways to go forward. Ollie Strachan, he led something in that cluster hire program from a few years ago. This was on uncertainty quantification, model-informed decision-making, and I think that's been fairly successful. I know that some others haven't been, though. I think I know some of the reasons why, but it can be effective, and these are cross-disciplinary hires. Anil Bajaj in mechanical engineering has been a big supporter of this and has helped to do joint appointments, which I'll talk about in a bit. We should not be afraid of joint appointments. Mike Manfra is my example of that. He's a wonderful colleague doing very well in the Burke Center. He's 3/4 in physics and 1/4 in engineering. Outside of Purdue, go look at Northwestern's material science and chemistry programs. They work together all the time. They're cross-listed all over the place. They're essentially the best in the country, I think. Yeah, and we don't have anything like that. And so I think that we should be, you know, this 107 new faculty slots in engineering, I think we should just say, we're open to having those, and maybe we have said, we're open to having those be joint appointments with science or education, whatever fits. This is one of my favorite things. The silly courtesy appointment system that we have, right? Why aren't we courteous by default? The places I think at Cornell, you don't need a courtesy appointment. If you're on the graduate faculty, you can advise a PhD student in any subject. Why aren't we courteous by default? I'd like an answer to that. It's not a rhetorical question. I think I've heard some answers, but they certainly aren't compelling enough to me. What you need, I think more of, are people like Anil Bajaj, department heads. Most of the issues here come down to the department head level. Sorry, I said down, like as if that's low, but they come to the department head level. And you have to have receptive department heads who really have the big picture in mind. It's the only way it works. It's the only way it works. So a final thought, and then I'm done. Taxonomy of research impact. This is just one taxonomy. It's certainly not the only one. The way I think about things, the way I'll think about how to do things going forward. Generally speaking, you know, I'm interested in this material discovery and synthesis and self-assembly. That's usually, you know, scientists, applied scientists, and what I consider myself to be on some days a misfit engineer. Then that's got to go somewhere, right? So if you have any engineering involved, it's got to go somewhere. So then you do property measurements, you do some modeling. That's the next thing, and that's the rich area of overlap between engineers and scientists. And then finally, you get to functional assessment and scale up, and that's where the engineers are in control. But also, that's where you also have to leave room for misfit scientists, because they want to play too. At least a lot of the ones that I know. So how does this look? I've just applied this to one of the things you heard about today. So here's Mehboob again, and here's Kyle, the granular mechanics. I could have done this for any number of things that I talked about today. But so we did a couple of things, and very, very basic. Athermal jamming, that means that it's zero temperature, right? It's very sciencey, right? And then we looked at how things stack and what kind of properties would come from those. These are both Phys Rev E, so they're still more on the science side. But then we took that and we went all the way into random assemblies of particles, jamming constructs for different boundary conditions, and then the transport in an application, right? This would be a hydrogen storage application, right? So that's what I see. And you don't have to do all three, but you should at least, whatever one you want to focus on, you should be, you know, inviting on both boundaries. Have your hand out on both boundaries. And along the way, I have to rib Mark, even though he showed up. You can get someone to force you to write a book, and you can agree to do it. And then, you know, Mark, I don't know. I'm just gullible. But no, if you think that you've done something that you ought to codify in something other than just journal papers, and we're academics, write a book. Anil Bajaj gets a shout out here because he wants his faculty to write books. Purdue used to be very well known for textbook writing. This is a graduate textbook and really more lecture notes. But yeah, I think that being an academic and writing educational materials is crucially important. I don't know if people in the engineering college think of this as engineering education, but I think writing a textbook is about the most fundamental thing you can do for engineering education. So here we are at the end. But it's really, for me, the end of the beginning. I'm going to be around another 20 years at least. And so, you know, I have I'm blessed with a wonderful group of people. This is a couple of years old, but most of them are still here. Going around the world, this is a trip to China that we did for NanoHub U. This is a group of folks from our sabbatical leave. This is when my kids were small, on our way back to the US at the end of our trip there. And so with that, I'll finish, and thank you for your attention. I know I took too much time, but I'll happily answer questions.
Yeah. I think what we'll say is that people who need to get to a class or another meeting are welcome to take off, and those who would like to ask questions, please go right ahead.
If there are no questions, I'm going to be hurt. So someone better, there's enough students in the audience they can ask.
Okay, I'll start.
Oh, thank you. Thank you, Shulin. Do you want the mic for the recording? Yeah.
Yeah. So I know you are very busy, you are very energetic. So I would just keep wondering, how can you manage your time and, choose your priorities? I think that's, any advice would be very useful for junior faculty also.
Yeah.
Yeah.
Yeah, so time management, I don't,
How many
my
hours
wife is laughing.
How many hours do you sleep every day?
My wife is laughing, yeah. So it's interesting. Right now I sleep more. During allergy season, I take some medication that makes me sleepy, so I sleep like 6 or 7 hours. Normally I sleep 4 or 5. Sometimes I'll go for a month or so getting just a few hours of sleep. But aside from the sleep, time management is, I'm not very good at it, so I hate to say much, but generally speaking, I think in a university you can find a lot of things that are not productive to consume your time, right? And I always joke about having so heavy meeting schedules with administrators and things like that. It's not really a joke. You have to say no to things that are low priority. So lately, I've been prioritizing getting in the lab. I've been in the lab for 5 to 10 hours a week, and people occasionally complain about that. Oh, I can't find you. You don't have time for me. I have time for my students, but other things. But I say I'm going to be in the lab. I put it on my calendar, and being in the lab is, to me, the most important thing. As far as student meetings, there's a couple things I've done, and I'll just end here. I don't have forced regular meetings with students. Instead, every weekend I put the available hours that I'll meet, and it's not open to anyone, that I'll meet with them and they sign up. If they have something to talk to me about, then they sign up. If they don't, then they don't, like when they have an exam, the week they have an exam. But if I don't hear from them for a couple weeks, then I'll ping them, like, you need to sign up for this. So that's kind of the way I do it.
Thank you very much.
Anil.
When are you getting into administration?
Yeah. So it's an interesting point. I can go back to Paul's picture. Paul asked me the same thing. And I said to him what I'll say to you. I've done and said and written so many politically incorrect things, not offensive things in the abstract or in general, that there's no way I could ever be an administrator. They would come back and get me. They'd come back, and I do it on purpose so that I won't ever be asked. I administrate all the time, though. In one way, I am in charge of the careers of a whole bunch of people who essentially work for me. Those are my graduate students, and to some extent the students in my classes. And I administer a group, and that's what I really feel like I was called to do, and that's it. Yep.
What do you have to do to switch the focus of your research from chimney flow to micro nano things?
It was not self-motivated. It was Ken Galloway who said, "Don't do it. Just don't even waste your time doing your old stuff." But the broader point on pivoting, right? So this is a startup company lingo, entrepreneurship word. They call it pivoting. I think that pivoting is very healthy even today, right? So I think I skipped through the SITMAV slide. I think I skipped right over it. But we started a new center in the past year for basically large-scale systems, aerospace systems. And that is something that is a pivot for me, where we're looking at system-level considerations and control, uncertainty quantification. So what do you have to do to pivot? And the number one thing is you have to go back to your roots and say, how did I attack the subject that I started my PhD with? And don't just do it that way. How would I do it better today than I did it back then? And that's more or less. So it's a lot of reading. It's a lot of testing hypotheses. It's a lot of building small prototypes, even if they're just sort of model prototypes, and then building up from there. Okay, I think there are no, oh, one more, Anurag.
It was nice to see your experience in different, like across the spectrum of nanotechnology. So having gone through so much experience, what advice will you give to a graduating student who is aspiring to build his career? What direction he should look forward to?
Well, I think that on the technical side of things, I would be focusing on scalable, and that's not a profound statement. I would do almost nothing that was characterizing a single nano object. I would try to be looking for important problems where collections of nano things have a chance, and that's sort of a scaling study you have to do, a chance of having a big impact on a big problem, and then looking at how the collective behavior of nano objects work together, because I think there's very few people really studying that. There's now a lot of people talking about that, but not so many people actually studying it.
Okay, so
Yeah.
I was going to ask you a question, but maybe you just answered it. Out of all of these really interesting things, projects you've been involved in, what are you going to do? What's the most exciting thing to you right now, and the thing you want to focus on? And did you just answer that? Is that what you're going to be
Yeah.
focusing on for the next 2 years?
Yes. So I mean, you can probably tell there's no such thing as focus in my world, unless you have like certainly stereo vision at a minimum. But I will be focusing on scale up and on the manufacturing process of scale up, and then all of the outlets that I built, whether it be thermal, electrochemical, even some of the things in control. I will be taking what we scale up and applying it to those in a way where we can do the statistics of the function. That's what I'd like to do. That's what we haven't done yet. So there's the subject of just scaling it up. That's the laser diagnostics, some of the process modeling, and some of the material characterization of when it comes out. But then applying it to real things. So that supercapacitor that was twisted around a glass rod and lit the LED, making more of those and understanding process variabilities and doing material discovery along the way. So there's a lot of things, materials that we can insert once we have a platform to do it with. Yep. And I want to work with Ashraf more. So whatever it's on. All right. Good. Thank you.
It's a wonderful talk.
Thanks.
I never heard